Osmosis is the spontaneous movement of a pure solvent, usually water, into a solution through a semi-permeable membrane. This membrane is selective. It only allows solvent molecule to pass through, but it prevents solid particle from crossing. The main driving force behind osmosis is the system's tendency to equalize the solvent concentration on both sides of the membrane. As a result, the solvent moves from a region of highest solvent concentration to a region of lowest solvent concentration until equilibrium is reached. Osmotic pressure, denoted by symbol pi, is the pressure that must be applied to the solution to stop the inward flow of the solvent. In other words, it measures how strongly the solution attracts the solvent. Osmosis has many important applications. It plays a vital role in the transport of fluid across cell membrane, help in medical treatment such as dialysis, and is used in osmometry to determine molar mass. Osmometry is especially important for measuring the molar masses of macromolecules such as protein and polymer, which cannot be accurately measured using other methods.
Next, we move to the fundamental of osmosis and equilibrium. In an osmotic system, equilibrium is reached when the hydrostatic pressure of the liquid column exactly matches the osmotic pressure. At equilibrium, the chemical potential of the solvent must be identical on both sides of the semi-permeable membrane. Then, the role of solute and pressure. In the presence of solute, it will lower the chemical potential of the solvent, while the application of pressure restores the chemical potential to its pure value. In simple arrangement, the entry of solvent dilutes the solution, making analysis more complex than in no-flow static arrangement where concentration remains constant. So next, we move to the 1/2 equation. For dilute system, the osmotic pressure is defined by formula pi equals to D in the column RT. Pi is mean the osmotic pressure, B is molar concentration of the solute, NB over V, R is ideal gas constant, while T is absolute temperature.
Next, we're gonna look on the justification of the Van Hoff equation. So this is a step-by-step justification of the Van Hoff equation, which is the osmotic pressure. So first of all, we're gonna look at the chemical potential of the pure solvent. So on the pure solvent side, the chemical solvent is at pressure as following on the slide. Next is we're gonna look on the chemical potential of the solvent in the solution. So in the solution side, there will be two effects that will occur. First, the solute will lower the chemical potential due to dilution, and next, the additional pressure will raise the chemical potential. Hence, chemical potential of the solvent in the solution is as follows. Then, since it's at equilibrium, the chemical potential must be equal. So we're gonna take the first equation and equal it with the second equation. Next, we're gonna look at the effect of solute. So since this is an ideal solution, so from the equation from the previous slide, we're gonna add the RT ln XA. Then we're gonna look at the effect of the pressure on the chemical potential. So we're gonna take the equation from the thermodynamics, then we're gonna integrate P to P plus pi. Then we're gonna get the following equation, where Vm is the molar volume of the solvent. And next, we're gonna combine the equation, and we're gonna substitute the equation into the equilibrium condition. So after that, we're gonna arrange it, and we're gonna get negative RT ln XA equal to the integrated symbol P plus pi, and the below is P Vm dP. That's all.
So, further on the justification of the Van Hoff equation, the additional pressure pi is required to restore the chemical potential of the solvent to its pure and re-establish equilibrium across a semi-permeable membrane. So for dilute solution, we got that ln XA is equals to ln 1 minus XB and equals to negative XB. Assuming a small pressure range, the molar volume of the solvent, Vm, can be treated as constant. Under this assumption, integration equation that we got is RT XB equals to pi times molar volume. Next, we are going to look at the mole fraction. For dilute solution, the solute mole fraction is Xb equals to Nb over Na, since Na times Vm molar volume equals to V, which is total volume of solvent. The expression simplifies to the Van Hoff equation for osmotic pressure. Osmotic pressure is large and easily measurable, making osmometry a useful technique for determining molar masses of macromolecules, for example, proteins and polymers. Real macromolecular solutions are often non-ideal. Thus, the Van Hoff equation is only the first term of a virial expansion. As we can see, pi equals to j RT in the bracket 1 plus Bj plus and so on. The constant B is the osmotic virial coefficient, accounting for non-ideal interaction in solution.
Okay, thank you for having me. Next, we will using osmometry to determine the molar mass of macromolecule. So by using Van Hoff equation, pi equal to BRT, we will combine it with virial equation, which is Z equal to 1 plus B TP plus CTP squared, and etc. So we will get the equation pi equal to JRT, 1 plus BJ plus CJ squared. But because we only have the data we will obtain will be linear, so we only use one parameter which is 1 plus bj. So we will move j into the denominator to obtain pi over j equal to rt plus brg. Okay, next then we will substitute j into c over m, which is mass over molar. So we will obtain pi m over c equal to rt brt c over m. And then we divided both equation the equation by m, we will obtain pi over c equal to rt over m plus brt over m squared c. Then we can see that we already obtained a linear equation, which is pi over c represent y, rt over m represent intercept, brt over m squared represent slope, and x and c represent the x-axis. Alright, so from the equation previous, we can obtain we can plot a graph which c over h over c. So from that we can obtain the y-intercept and so.
Now, let's look for the calculation. The data give the following value for the quantities to plot: mass concentration and the value of H over C. The points are plotted in the graph, and if we look on the previous graph, we can see that the intercept is at 0.2. So we can calculate the molar mass using this equation. So we can just substitute the value into the calculation, and we will get the answer, which is 1.2 times 10 power of 2 kg per mole. So we use 1 kg meter squared per second equal to 1 joules. The molar masses of micromolecule are often reported in Dalton with 1 Dalton equal to 1 gram per mole. The micromolecule in this example has a molar mass of about 120 kilodalton. Because of the modern osmometer give the reading of osmotic pressure in Pascal, so the analysis of the data is more straightforward. Last but not least, let's do this self-test. So we need to estimate the depression of the freezing point of the most concentrated of each solution, taking the constant value as about 10 kg per mole. So all of these four is the given data from the example. And firstly, we need to calculate the mole solute using this equation, and solute equal to C over M. So we just substitute the value into the equation, and we will get 7.5 times 10 power of minus 5 mole per pm cube. And then we need to calculate the volume solution using the equation density times volume, and we will get 780 gram for the volume solution. So mass solute is 9 gram, and the mass solvent is 0.971 kg. After that, we need to calculate the molarity using the equation m equal to n solute over mass solvent in kg. So as usual, we just substitute the value and we will get 7.72. So lastly, we using the equation of depression of the freezing point that equal to constant value times molarity. And we will just use the value of molarity that we calculate into the and substitute to this equation, and the final answer we will get 7.72 times 10 power of negative 4 k, or we can run off into 0.772 mk.